Hi guys, this is Math 148 section 10.1. So in this chapter you're going to be doing a whole lot of graphing and essentially using your derivatives to figure out the various elements of a graph of a function. So in section 10.1 we are using the first derivative to find what the book calls the critical values, which are really the maximum and minimum. So we're going to use the first derivative to find critical values, and then we are going to learn whether these critical values decide if they are maximum, a little relative maximum, or a relative minimum. Now what this is trying to say is fairly intuitive if you have a graph. So if you were to be given the graph of a function, this is example 1 in your book on page 641. All right, now I won't write on this, it'll get stressed out. But here's the graph of this function. Here it is right here, example 1. In your book. So if you wanted to find the relative minimum, the critical points, what they're talking about are these places where the graph changes direction. Some people call them turning points, but critical point is what the book has decided on. So here's one here, right? It changes direction here at -2 and then 2.667. It changes direction here at 0 and 8, and it changes direction down here at 3 and -7.75. This one's a minimum because it comes down and then it goes up. That's a relative maximum, and that's a relative minimum. We say relative because it's not actually the maximum because it goes up for infinity, but it's a relative maximum right here. It went up and then it came down. So it's like a minimum, maximum, minimum. So if you have the graph, it's fairly easy to find, but the question is, if you just have this function, how do you find these points using calculus? Why would you use calculus? Because you're in a calculus class, my friends. So let's look at question number 9. This is one of your homework problems. This is how you do it. You have a function, y equals 2x to the 5th plus 5x to the 4th minus 11. And the book tells you to find the critical values. I'm trying to read it exactly. Find the critical values and then make a sign diagram and determine if they are relative maximums or minimums. So the first part, find the critical values. This is something you need to be able to do for your test. Find the critical values and determine if they are maximums, relative maximums, or minimums. So to find the critical values, you take the first derivative. So this is 10x to the 4th plus 20x cubed. See how those derivatives work? We just cruise right along. And now to find the critical values, you set the first derivative equal to 0. Now, if some of you really want to know why that's happening, it's because the first derivative is the rate of change. It's the slope. So when the slope equals 0, right, there's a straight line here. It's going to be 0 there, 0 there, because the rate of change is 0. So anyway, we're setting the first derivative equal to 0. We're saying which x values are going to make the first derivative equal to 0. So in order to find the x values that make this equal to 0, I'm going to factor it. So I get 10x cubed and then x plus 2. Do you see I factored out a 10x cubed from all this? And then I say, what x values make this thing equal to 0? Well, I will tell you. It equals 0 when x is equal to 0, right, that piece, x equals 0. And if this equals 0, you get x equals -2. I skipped the step. That would be x plus 2 equals 0, x equals -2. So these are the critical values. That's part 1, find the critical values. There they are. Now this is just the critical x values. It's not actually the whole point, the critical point. So now we want to use our sign diagram to determine if these are maximums or minimums. I'm going to pause it and get a new page. Okay, so I rewrote the problem here. We found the critical values where x equals 0 and x equals -2. And again, we found that by saying, when does the first derivative equal 0? That's the critical values. Is when y prime equals 0, that gives you the critical values. CV, Crescent Valley, that's where I went to high school. Pretty cool. So in order to do this, here's how the sign test works. I draw a line like this, and you put your two values on the line. So I'm going to put -2 down here, because it's negative, and then x equals 0 up there. Okay. Technically, you don't have to draw a line, but I find it easy, might as well. So now we're going to pick a point on this side of x equals -2. So I'm just going to pick -3, for example. It could be any point. And then you evaluate the function, so it is y, f prime. I'm saying f prime, I should say y prime. get out of there, y prime, no tools, I don't want you, of negative 3. So I'm going to plug negative 3 into this function. So that's 10 times negative 3 cubed times negative 3 plus 2, right there, so I'm using this. You're plugging negative 3 into the first derivative, and that gives you 270. So the value doesn't matter, but what matters is this is positive. So I put positive there, like that. Now I'm going to pick a number in the middle between negative 2 and 0. You could pick any number you want, but I am lazy and like to pick somewhat straightforward numbers, so I'm going to pick negative 1. The simplest number between negative 2 and 0 is negative 1 in my mind, so I plug negative 1 into the first derivative, not the function, but the first derivative, and I get negative 10. Sorry, I sped things along. No worry, Fuji driver. So that's a negative number. Right there, it's negative. Really all you're interested in is the sign. Now we pick one on this side of 0, so I'm going to pick 1. Could be any number over here. I'll just pick 1, pick negative 1 here. Pick 1 there. So the first derivative, this thing right here, put 1 right there, get 10 times 1 plus 3, okay, that's 30. And that is positive. So again, you're looking at the sign of the derivative. What direction is it going? So what this tells you, and this part's sort of fun if you like to draw arrows, is that the function, this function right here, is moving up, and then it gets to negative 2, and it goes down, and then it gets to 0, and it goes up, because these signs are telling you slopes, they're telling you directions. Because the first derivative is the rate of change. It is the slope, the direction that the function is going. So now we know we have some function that goes up, it hits negative 2 and it goes down, and it hits 0 and it goes up again. So because it goes up and down here, this is a maximum. Do you see that? It goes, whoa, like that. So it's a maximum because it goes down then up, whoa, like that. That is a minimum. So here's how you write this out. You say we have a relative maximum at x equals negative 2, and that is the point. You can't just write negative 2. You want to find out what the point of that is on the graph. So when y, you got to use the actual graph now. When y is evaluated at the point x equals 2, you plug 2 into this equation, right? That's 2 times 2 to the 5th plus 5 times 2 to the 4th minus 11 equals 5. How did I get 5 so fast? I did it ahead of time. Oh, but you know what? I'm actually plugging in negative 2. Negative 2. Negative 2. It's still 5. So the point is negative 2, 5. So you say there's a relative maximum at x equals negative 2, or that is a relative maximum at the point negative 2, 5. We do the same thing for a relative minimum at x equals 0, which is the point 0. You plug 0 into here, 0, 0, you get negative 11. So when you're finding the points, you always want to use the original function. So you can actually find the point on the graph, not the point on the first derivative. So I'm saying, suppose you were stuck on a desert island and you had to graph this function, because that's what happens when you're stuck on desert islands. You could find the maximum by plugging in the maximums at negative 2, 5, and the minimum at 0, negative 11. And when you get back home, you can check this on your graphing app. And that's negative 2, 5 is a maximum. It goes zoom, and it comes down, minimum at 0 and negative 11. So there's one more thing that I want to show you about these. In general, you should be able to use that first derivative test to find the critical values and then say whether they're maximum or minimum. But there's a nice little picture. Look on page, oh shoot, I missed it. I turned the page. I'm flipping, here it is, page 640. Where it says you could have a relative maximum, looks like this, if you have the derivative is going up, it goes down like that, here's that relative maximum, f prime of x, its derivative equals 0. But if the derivative is undefined, if f prime of x is undefined, you might still have a critical point. It'll just, the graph looks like that. See? You might want to look at the picture, it's much nicer. And similarly, if you have the function where you have some derivative is the function evaluated, the derivative equals 0, right? And you see that it's going up, you do that same sign test, and going down, then this is a relative, oops, did the same way, you guys, honestly, like that. If it goes down and then up, and the derivative equals 0 here, then this is a relative minimum. But if you do your sign test, then you have that it goes down and then up, but f of x is undefined. If it's undefined, then you're going to get this weird thing that looks like this. Maybe something looks like that. Boing, like that. That's the function might look like this. So sometimes you get the derivative is undefined. What would that look like? Square root of x, something like that. Suppose the derivative was square root of x, then it would have some undefined points. Or 1 over, x, something like that. So just be aware that sometimes critical points are also places where it's undefined, and it's not just places where the first derivative equals 0. So with that said, do check out page 640, kind of study that picture for a second, and then work on your homework. Good job, guys!